All right, welcome back, everyone. Hopefully, you all can hear me. So we'll be getting started a little bit. Just some announcements. Lab 5 post lab is due by tonight, 11:59 p.m. So make sure you turn it in before then. But if you're like a few minutes late or uploading error or something, that's fine. I won't mark you off for being late. But just try to turn them in because the late penalty is a certain percentage of the total points, and it's a lot. So you don't want to do that. Okay, so this week we are talking about experiment 8. Before we begin, are there any questions? Any questions? Okay, I'm going to share my screen right now, and let's talk about this week's experiment. Okay, so today we're going to be talking about natural product chemistry, basically isolation of caffeine, a main component of the stuff we use or we drink to help us stay awake. So let's talk about what this experiment is about. So the objectives, of course, natural products, where caffeine is from. It's from a natural product. Extraction. We have talked about extraction before, so this might be a little bit of review. Sublimation, that's a new purification technique we're going to be learning today. And then lastly, green chemistry. So chemistry these days are leaning towards more greener methods, and this lab is an example of how we adapted to a green procedure. Okay. So caffeine belongs to a class of products called alkaloids, and they're natural products because they're compounds that can be obtained from living organisms such as plants. And from tea leaves, caffeine can be obtained from tea leaves. So that's where we're going to be extracting our caffeine from. Alkaloids, if you're ever wondering, is basically a class of compounds that are found naturally, and they contain at least one nitrogen atom. As you see here, caffeine contains 4, so it looks like a compound that may be kind of like psychoactive. Many amines or stuff that has amines in it tend to be psychoactive. So caffeine certainly fits the bill there. Okay, so that's caffeine. That's the structure of caffeine. Looks a little bit complicated. Let's go on. So extraction. So we talked about extraction in experiment 11. If people can remember, where we extracted our organic layer from the aqueous layer using I forgot what it was, but we used an organic solvent to do that. So here we're going to do the same thing. We're going to be extracting again, but this time it's a little bit harder because both solvents won't be colorless, so it'll be kind of hard to distinguish the two of them, because your extract, or the thing you extract from the tea leaves, is going to be dark and kind of gross. The miracle is we can actually extract caffeine from that big mess of a mixture, and you'll see that in the lab for today. Okay, so extraction, we use a compound solubility for one solvent over the other to extract and isolate it from a mixture and make separation easier. So this usually involves an aqueous solvent and something organic. So caffeine is somewhat soluble in water, but not really. So it's going to be more soluble in something organic. So that's we're going to use an organic solvent to do that. So watch the video about the principles of extraction for review, so you understand, how we use this in the daily basis to extract things during chemical reactions or after chemical reactions. So this is a review of extraction here. Okay. So let's talk about extracting caffeine. So we're going to put in a solution of sodium carbonate. So why do we use sodium carbonate? Well, first, it ensures the acidic components, the tannic acids. So tea has lots of things called tannins, and they're this big molecule, and it's acidic. So we need to make it basic, so we can extract this in extract the caffeine away from the tannins, which will be soluble in the water phase or the aqueous phase. And so we ensure that the caffeine, remember we said caffeine is the structure like this. We ensure that the caffeine is not protonated, because if it's protonated, it'll probably be soluble in water. So we don't want that. It has lots of electronegative atoms, so it gains a positive charge. It's going to be more soluble in water than our organic solvent. So we don't want that, because we want to separate it. So we are going to make sure it's not protonated and remains as the free base. So the carbonate also reacts with tannins to form a salt, so that makes it more water soluble. So that makes our lives easier, and it makes the solution moderately alkaline. So that's a good thing, because we want to make sure it's neutralized. So we don't want this caffeine being protonated. Okay, so that's why we use this carbonate solution. So you may know, like, when we ever put a tea bag in water, we extract the tea from the tea bag, right? From the leaves. So the caffeine and all the tannins get extracted into the aqueous phase whenever you make hot tea. So you could do it in water, but this process makes it much faster that we isolate the caffeine for our purposes. Okay. So that is the purpose for our solution. So that's how we would heat up our tea bag in this aqueous solution, and then over time we would get a saturated solution of our caffeine and the tannins, and that's how we go from. Then the next step is purifying the caffeine. Okay, so all right, here's a question for liquid extraction. Okay, let me just invite the people. Sorry about that. So for liquid extraction, what solvent do we want to use? So what solvent do we use to extract? Is it DCM? Is it water? Is it methanol? Is it DCE? Or is it the other solvents? Any ideas? So what solvent do we use for our extraction? So probably not water, because we already have water in there. So adding water won't do anything. So the what we want to use is DCE. So we use DCE because it can actually dissolve caffeine. Methanol won't do the trick. It's not organic enough. So we either use DCE or DCM. DCM is also a good choice, a popular choice. However, it's highly more toxic than DCE, so we choose DCE for its lower toxicity, but DCE is still considered toxic. So pretty much there's not much of a trade-off, but in terms of safety, DCE is better. Okay. So we use DCE because it can dissolve the caffeine, just the caffeine, but is less toxic than DCM, so that's why we use it. So for this extraction, since you're going to have a layer that's considerably looks like swamp water, it's going to be hard to separate the layers or see a separation. So you have to be careful how you mix the layers when doing the extraction. So in your separatory funnel, you want to use a rocking motion. So like rocking a baby to sleep or something, like rocking side to side and not shaking it like you would do for like a cocktail. Or for making an actual coffee drink. You don't want to shake it. You don't want to shake the separatory funnel, because you'll create emotions, and those emotions will cause the layers to not separate completely. So there's a video about the extraction process. So I suggest you watch both of them and see what happens when you do a rocking motion and when you shake the separatory funnel. They'll produce two different results. And the shaking one is probably the one most students would run into, because they don't rock it, and they think shaking it is more efficient. But in terms of experiments like these, they're not. So we want to use a rocking motion. But it's too bad, because you can't even do the experiment. But you'll get experience of to see how it's done. So that's at least something. Okay. So let's talk about which layer is where. Where is the organic and where is the aqueous? Okay. So So water is actually less dense than DCE. DCE is more dense. So you gotta ask yourself, will it appear on the top layer or the bottom layer? So remember, if something's more dense, it'll be heavier, so it'll sink to the bottom due to gravity. So in this case, it's going to be the aqueous layer will be the top layer, and the bottom layer will be our organic, which has the DCE. So top layer will be water, and the bottom layer is our organic layer, caffeine. So compare the densities of water and DCE. So halogenated solvents are usually heavier than normal hydrocarbons or water. So they tend to be really dense. Okay. So this procedure is the same as experiment 11. So a lot of these steps are the same, especially when we dry the organic layer afterwards with sodium sulfate. A lot of the steps are the same as in experiment 11. So we've seen this before. So it shouldn't be completely new. Okay, so we're coming to the end almost, so stay with me for a bit. So filtering and drying. So after you isolate the layer, some solid particulates may come through. So you want to filter off the solid particles. You also want to filter off the drying agent after you're done. So this is another way to filter it. So that's why we're filtering it, to filter off any solid particulates that got in through the extraction process, and to also filter off the solid drying agent. So we want to make sure our organic layer has no water in it. So we want to make sure it's completely devoid of water. So we add a drying agent. So we did that last time in experiment 11 too. So watch the filtration video for more info and more details about how to do the filtration. So we're going to dry by evaporation. So this is, we're going to dry by heating the organic layer. So we're going to evaporate the organic solvent slowly until the caffeine precipitates. So we do this in the fume hood because DC is so toxic. We don't want people breathing it in the room. So we make sure we do this in the fume hood. So our caffeine will then, there's no solvents, so our caffeine will no longer be soluble and will precipitate out as a crude solid, and we can isolate that material. So usually this type of evaporation is way too slow. So usually in the lab, we use something called evaporation under pressure, or rotovap. And that's how organic labs isolate their materials on a daily basis. We use evaporation under reduced pressure, because under reduced pressure, the boiling point of DCE will go down, so we can evaporate it much more quickly and at lower temperatures. Because if you boil it if you evaporate with heat, you can decompose your product, so that's also a downside. But in this case, it's not an issue. Okay, so that's our filtering and drying. So see, there are a lot of steps that comes with isolating natural products. So it's always a stepwise ordeal. Okay. So the last thing we'll talk about is the purification process, sublimation. So sublimation is when we go directly from maybe a crude solid, we heat it, then it sublimes to the gas phase. So it evaporates directly to the gas phase. That's called sublime. And then once it hits the walls of so we're going to heat it maybe with a burner, and then the cold areas of the test tube, once the vapor reaches those areas, so obviously we'll have to plug the top, because if we don't plug it, the caffeine vapors might just escape. So once we plug the top with like a cotton ball, the vapors will have nowhere to go. So it'll hit these walls of the test tube, which is much cooler than the bottom where the flame is. So it'll deposit it back to the solid phase, and then these particles right here are supposed to represent the purified crystalline caffeine purified caffeine. And at the bottom, what you'll see at the bottom, what's left is the crude brown material, or your impurities. Okay, so just to recap, we could do sublimation if our product is volatile, but our impurities are not. So we want our impurities to remain at the bottom. near the flame because we don't want it to separate with the caffeine. So like recrystallization, the caffeine will vaporize. Then once it cools, it'll go back to the solid and deposit on the sides of the flask, and you'll see nice white crystals. So and this effectively leaves the impurities at the bottom, and on the sides of the test tube, you can collect your purified caffeine. So caffeine is actually a colorless solid. So there's also a video about sublimation, so make sure you watch that. Okay. So where is the caffeine? Well, as I explained, it is the crystallized white solid on the sides of the test tube. You'll see that in the video as well. What's left behind? So it's mainly impurities, and I think it's tannic salts that may have gotten in the organic phase. Other than that, I'm not sure what else it could be. Besides other impurities from the tea bag or the tea leaves. And so why no solvent? So this is the beauty of this experiment. It's green chemistry. So we tend to try not to use solvents if we can, because many solvents are, they get wasted. You generate waste to treat it. And most of the solvents are toxic to the environment. So if we can use no solvent, the better. And that's what we can do here, because remember, sublimation does not require any solvent. We just have to heat the solid and it'll go directly to the gas phase. And whatever's left behind will remain. So we don't have to worry about treating the impurities if we use the solvent. Okay. So lastly, we're talking about waste disposal. Waste disposal is also a measure of how green your experiment is. So if you generate a lot of waste, not a very nice environment, because you have to treat it, and that costs like resources. So if you generate no waste, that's best. And it's best if you just generate like non-hazardous waste like water and like air. But so we wash with water because we're going to rinse down the filtrate from the separatory funnel down the drain. But what do you do with your product? Once you collected the caffeine, you just turn it into me. If we were doing this lab, you just turn in your test tube to me. The waste. So initial waste, since initial waste has DCE, you need to drain at least 10 mils and put that in the waste container. The other waste is from the tannins from tea leaves, and they're not really toxic. It's pretty much all in the aqueous phase, so that could go down the drain in the fumehood. But we can't dump it down the regular drain outside the fumehood because it may have DCE in it. So we must drain it down in the fumehood, and then we just rinse with water, and that's it. Okay, everyone, that is it. If there are any questions, let me know. I'll stay back to answer any questions, maybe about the post lab some people may have. Other than that, thanks for listening, and I'll see you next week.